So last time we finished the Coulomb screening effect and also the plasma oscillation physics. Today we start a new chapter, which is the second quantization for bosons. As we already defined in the very beginning of the lecture, we need to second quantize both the fermions and also bosons. And then we first introduced the second quantization for fermions, and so now we should do the same for the bosons. As I already pointed out in this diagram, that if you use occupation number basis for bosons, then we could sort of construct a vacuum state where there's no boson, and single occupied boson state and double occupied boson state, and so on and so forth. So there's no upper limit for the occupation number for bosons because there's no such a Pauli exclusion principle applied to bosons, and bosons would like to condense. It's called Bose-Einstein condensation, and we will explain this phenomena BEC, Bose-Einstein condensation, after we introduce the second quantization operators for bosons. This is the general eigenvalue equation for occupation number basis, and this n with a hat represents the number operator for a particular quantum state nu j. When the x on this state n nu j, you get eigenvalue, which is the occupation number n nu j times the state. Okay, and this n nu j could be either 0, 1 for fermions, but it could be 0, 1, 2, up to infinity for bosons. And we are talking about this bosonic case. Since these bosons do not have such a Pauli exclusion principle, they behave symmetrically if we exchange this two bosonic wave functions. All right? Okay, so as you already learned in quantum mechanics, that if we exchange two electrons wave functions, the total wave function gets minus sign, right? However, if you exchange two bosons, you don't change the total wave functions. There's no such a minus sign. It's a plus sign for bosons. And remember, because of this minus sign, under such exchange for fermions, you get anti-commutation relations, right? You get the anti-commutation rules. Ci and C dagger j refers to the destruction and creation operator for fermions, with the index I and j referring to this quantum number or some labeling for the states. However, if you exchange two bosons, don't get the minus sign, it's the plus sign. As a result, you will see later that this boson creation and destruction operator satisfy so-called commutation relations, meaning it's not the anti-commutator that we are familiar with for fermions. Instead, it is a commutator, just like the commutation relations for X and P in quantum mechanics. Great, and we will check this property, but of course we should impose that sort of assumptions. That is the commutation relations for bosonic second quantized fields. Okay, and the origin of such commutation relations is precisely the symmetric total wave functions for many boson systems under exchange. And this is our starting point. That this when we define this bosonic creation and destruction operators, we need to have such a properties that under exchange, they don't get minus sign. It's a plus sign. So now you know the difference between this anti-commutator, the bracket, and the bracket for the commutator, right? So anti-commutator defined as AB plus BA, and the commutator is defined as AB minus BA. Okay, so if this commutator between A and B vanishes, which means that AB acting on any state is same as BA, which is equivalent to say that this many boson wave functions are symmetric under exchange. And if AB plus BA acting on any state vanishes, which means that AB as an operator shows a relative minus sign to this BA, which is equivalent to say that this, two fermion wave functions under exchange will lead to the minus sign. Okay, is that clear? Good. So now we could define our bosonic creation operator B dagger nu J acting on this occupation number state, where in the states we have many different quantum states with corresponding number of occupation and nu J. And in particular, if we like to increase the occupation for particular states, say nu J, by applying this B dagger operator, then we get the final state where all the occupation remain the same except this nu J, you should add 1 onto that state, nu J plus 1, which means that you have one more bosons added in that state. Okay. However, just like the definition for creation of fermions and destruction of fermions, there is a prefactor. Remember, in the fermionic case, we get a minus sign to some power, right? This power is the sum over this occupation from this very first particle or state up to the particle that's just left of that state, right? Here we get a similar but different situation because we still have to calculate this prefactor. Of course, the prefactor will be different from this fermionic case, and this is our job today. Okay, to fix this prefactor B plus, which is a coefficient in front of that final state when we add one more boson. Okay, likewise, you get B minus coefficient in front of this destruction of one boson operation. Okay, so once you destroy a boson in this many boson state, particular state, say nu J state, and the final state will be that state where this nu J becomes nu J minus 1. With the proper prefactor B minus, of course B plus is not the same as B minus, and we need to figure that out what they are. Okay, so of course we need to impose such symmetric wave functions of many boson states because of this commutation relation, or because of this symmetric total wave functions of many boson systems. So since bosons are symmetric, that is, if you calculate this commutator for B dagger nu J and B dagger nu K, you got 0. For all this quantum state, nu J is not the same as nu K. Okay, so this is the equivalent statement to say that under exchange, these two boson wave functions remain the same. Now you could make this analogy very easily that if you create something and in the Schrödinger picture, you create some wave function, right? Something like that. Okay. So if there are two operators here for creation two bosons in different states, that means you have two bosonic wave functions. And this commutation, this kind of symbol refers to the fact that you need to exchange, right? Okay, so it is what AB minus BA. Okay, so it is equivalent to say that this is precisely this situation that you have two bosonic wave functions multiplied together, and one is phi I phi j, another is phi j phi I. So you move the right hand side of phi j phi I back to this left hand side of the equation, so you get phi I phi j minus phi j phi I, which is 0. Okay, so this is precisely the case here. So it's just that we use a second quantized fields to represent a bosonic particle. So you can consider this just a wave function. the Schrödinger wave function. Okay? And so this is the condition that must be satisfied if there are bosons. When we define this kind of creation and destruction of bosons, we didn't know that. Okay, so we need to impose that conditions separately, independently, to really guarantee that these operators, B and B dagger, really refer to bosons because they need to satisfy this commutation or symmetric single particle state. If you take the Hermitian conjugate or complex conjugate, the creation operator becomes the destruction operator. Remember that. And they also satisfy this commutation relations. Okay, so this is the first commutation relation, and this is the second commutation relations. Okay, so I should say this is commutation. So what about the third one? So remember, in the fermionic case, we got CICJ and CI dagger CJ dagger and CICJ dagger with any commutator, right? Here's the same. You got the commutation relations between two dagger operators, two non-dagger operators, and one non-dagger and one dagger operators, right? So the third commutation relation should be B nu J and B dagger nu K or nu J. So let's just try to calculate this first. Suppose you have one destruction operator, B nu J, another creation operator with the same quantum number, B dagger nu J, and you want to calculate this commutator between these two operators. So what do we do? Of course, we need to fix some coefficient, at least from the start. A starting point, if we have an empty state from the start, and we can start to create single boson state by applying B dagger nu. We can also destroy this single boson state and get back to this empty state or vacuum. So we know that we cannot destroy the vacuum state anymore by applying a destruction operator, as I mentioned here. And this is also the same for fermions, right? If you start from the empty state and you want to destroy nothing, you get zero, because nothing is nothing. So you cannot destroy nothing. There's nothing that you can destroy. And therefore, if you want to destroy nothing, you get zero. Okay, so this immediately tells you that B minus, of course, this B plus and B minus coefficients are functions of this occupation, because you obviously see that depending on what its occupation number is, this B plus and B minus coefficient will be different. So they are functions of occupation. So let's start from the vacuum state and use J is 0. So, but if you destroy this state 0, you get 0. Okay? Of course, 0 is actually 0 times state 0, right? Okay, so therefore, you immediately check that this is the first coefficient that you could get, which is B minus 0. Okay? Which means that if N u J is 0, then if you destroy this state 0 here, you get state 0. So B minus 0 is 0. Because the prefactor is 0 if you start from the state, vacuum state, and you want to destroy the vacuum. Okay, so we fix the first coefficient. So now we can start to build our coefficient towards from the bottom layer, right? Okay, it's like a pyramid, and we start from the bottom and we try to increase this occupation one by one and calculate B plus and B minus accordingly, and then we know the general rule for B plus and B minus. But that's the next job. So we can also create a single boson state, right? And we know that this will be a coefficient B plus 0 times the state 1, single particle state. So, but we can fix this coefficient B plus 0 to be 1 to normalize this coefficient, because we know that this cannot be 0. Okay? Because if you create a particle from nothing, and you get single particle state with the proper coefficient, and that coefficient could be normalized to 1. So we just take this as a normalized value for b plus 0. Okay, so we get 2 coefficients already. So let's just start from here and build another set of b plus and b minus if you want to increase the occupation number by 1. So let's just do the following algebra. Okay, suppose I have state 1, single particle state, and I sandwich this state 1 and state 0. Inside this bracket is the b dagger operator. Suppose that I create a single particle from a vacuum on the right. So then we have a single particle state on the right, which is the Dirac-Kat state. But on the left-hand side, this is the Dirac-Bragg state. Of course, it's also a single particle state, and therefore this is finite. This is non-zero. And we could fix this value, calculate what it is. And you could change this so-called matrix element by this conjugation. Okay? So if you apply this Hermitian conjugate of that matrix element, you get back to this one. But we could start from here because this will lead to a non-trivial result. And this immediately tells you that this b minus 1 is actually 1. So why? Because this is what? So if you destroy the particle, a single particle state, a single boson state, by applying this b nu j, you get what? B minus 1 times 0, right? But b minus 1 is actually a coefficient. So therefore, you get what? B minus 1 times 0 on the left, Bragg state, and 0 on the right, the Kat state. But this vacuum state is actually normalized. So this matrix element is actually 0, 0 is actually 1. And therefore, you get b minus 1. Okay, on the right. What about on the left? Okay, so let's just continue doing the algebra. So as I mentioned, if you increase the vacuum state by adding one more boson there, so you get 1 times state 1. Okay, so this is 1 times state 1. Okay, so since this b plus 0 is actually 1, so let me just write it here. So b plus of 1 is actually 1, and therefore this is what? This is 1 on the left and then 1 on the right. Okay? What is this? Okay, so this is simply just 1. Okay, so you simply connect this, the very right from this lengthy equation and the very left and they are equal. And therefore, b minus 1 is actually 1. All right, good. So let's take a short break. When we come back, we will, based on this coefficients, simple coefficients, in state 0 and 1, and we could check whether this commutator and what that value is for this commutator, and we will see in just a moment. Okay, so based on this b plus and b minus coefficients for this empty state 0 and singly occupied state 1, we could check what this is and calculate this commutator between b nu j and b dagger nu j. And of course, this product between these two operators are still operator, right? So there are two operations. One is b dagger b acting on some state, and another is b dagger acting on some state. Okay, so I can choose the states, any state I like. For simplicity, I simply just choose this, the state that this operator acts on to the empty state. Okay, so first I apply this b dagger b operator and acts on the state 0, and you know very well that this is 0 because you should start from the first operation, which is the destruction of a particle, a bosonic particle, from empty state 0, and you cannot destroy nothing, and therefore this is 0. And the second operation is the reversed product, which is b dagger. You first create a single particle out of nothing, and then you destroy that single particle state. You go back to this empty state, but this is non-zero. Okay, as I mentioned, this is what? This is 1 after the first operation, right? And then you destroy this single particle state by B nu j, and you get back to state 0 with the coefficient 1, and that coefficient we already obtained, right? We already derived that B plus B minus coefficient. Okay? All these coefficients, if they are non-zero, are 1. Okay? So, and therefore, you go back to this empty state with the prefactor 1. Okay? Clearly, they are not the same, because 0 is 0, a number 0, but 0 with the Dirac state refers to the empty state. Okay? So, the empty state is not equivalent to 0. Of course, on both sides, 0 appears. But remember, on the left-hand side, this is the quantum state. On the right-hand side, this is the number. Okay? The number is a number. A state is a state. Of course, the number 0 times state 0 is still 0, but the state 0 should be 1 times state 0. Okay? So you could roughly consider this as just 1 times state 0 differs from 0 times state 0. Of course, they are not the same. Okay? But the difference between the two is actually 1 times state 0. Right? You can simply just take the difference between these two operations. You get, and acting on the state 0, you get 1 times state 0. So, of course, you can actually make this a general statement that I don't care what the states that I apply to, so they're always satisfied. This is 1. So I simply just remove the quantum state and simply look at this, this identity of this operator acting on any state should be the same, which is 1. And this is the final, this commutation rules. So let me summarize these 3 commutation rules. But before I summarize, there's homework that you need to check. This identity holds for arbitrary, for any state, n u j. Meaning, I don't need to just do the algebra with the initial state being empty. I can also use, say, state 1, state 2, any arbitrary state with any arbitrary occupation. And this statement is also the same, that this identity is still there. And therefore, you need to use different starting points, or you need to use different states, such as state 1, and you check whether they are the same, and so on. So of course, you need to figure out this B plus and B minus coefficients before you applied n equals to 10, for example, because you need to know this B plus 10 or B minus 10 coefficient, and we don't know that yet, but we will derive the general expression for B plus and B minus just a moment. But let me just summarize the commutation relations. For bosonic operators, B plus and B but B nu J B Lec nu K is actually delta nu J nu K. Okay, so I leave this to you as another homework to prove it. Okay, so this is not the same homework as this, because you see this, the first homework involves this commutator with the operators having the same state indices, right, nu j. But here, they're not the same necessarily. So B nu j or nu j is not the same as nu k necessarily, so they can be the same, but they can be different also. Okay, so, but if they are the same, you get 1. If they are not the same, you get 0. Okay, so this is a different exercise. But to prove this is really a piece of cake, just one line. You just assume that they are not the same, and you could actually do the same algebra, and you immediately show that they are delta function. Okay, great. So intentionally, you don't need to memorize, but you need to remember this very important commutation relations for bosonic operators, which will be repeatedly used in our further discussions. Okay? And these three relations are general for arbitrary initial states. Now, so let's just fix this coefficient b plus and b minus. Okay, of course, we need to show some commutation relations between these number operators and nu and this either B or B dagger operators, as we already studied for fermionic case. So we define this number operator for bosons the same way that we define for fermions, which is B dagger B, but carrying the same quantum numbers, nu, which refers to the number operator for that state, and the eigenvalue refers to the occupation number for that state. So now, since we have such commutation relations, we could further check the commutation relations between a nu operator and B or B dagger. Okay, and why is that important? You will see later. Okay, so this is a very important commutation relations for bosons. So first, when we evaluate a nu commutator with B nu, you get minus B nu, and nu commutator with the B dagger nu, you get B dagger nu. So let's check these two relations. Okay, first, we evaluate commutator between N nu and B operators. You could simply just spell them out. N nu is actually B dagger B. So you got a B dagger B on the left of the bracket commutator and B nu on the right. So you must know this commutator between one product, which is on the one side, this is the product of the two operators. On the other side is the single operator. So this ABC commutator is going to be A times BC. All right, so you should know that from your quantum mechanics course by now. Okay, so you could check this, whether this is really identity. So let's just apply this rule, identity, and you get B dagger nu, B nu plus B dagger nu, B nu, B nu. Right? So let's just calculate one by one, and the first term, which is the B dagger times this BB commutator. Okay? So, of course, a commutator of the same operator, you get 0 because AA minus AA obviously is 0. And what about the second term? Well, this is B dagger B. Remember, the standard conventional form for the commutation relations involving one B and one B dagger is actually commutator between B and B dagger is actually delta function. Okay? So, of course, the commutator between A and B is minus BA commutator. Why? For simple algebra, this is BA minus AB with a minus sign in front, which is AB minus BA. Yes? Simple algebra. So if BB dagger commutator between B and B dagger gives you 1, then B dagger B commutator should be what? Minus 1, right? And this is just a number minus 1 times V mu, which is this. Check. Okay, so now you know it's your job to prove the second identity. That instead of B nu, you calculate the N nu B dagger nu commutator, and you get a plus 1 times B dagger nu instead of a minus V nu. But you know the procedure is actually the same, but you need to take care of this from these commutation relations. Great. So, and these relations are very important to get this coefficient B plus and B minus. Okay, so let's take a short break. When we come back, we will, based on this result, to actually fix this coefficient B plus and B minus. Okay, so let's fix this B minus coefficient first. So as I mentioned, we need to take advantage of these three relations. The commutator relations between N nu and B nu, and also N nu and B dagger nu, and also the eigenvalue equation for the number operators N nu. So let's just do the algebra. Suppose that I destroy this boson operator. I apply these boson operators and destroy a boson number by 1. So I apply this B nu operator onto this N nu state, and I square this. Of course, in quantum mechanics, square refers to this Dirac-Broglie state on the left times Dirac-Katz state on the right. Right? So if you square this, and this is simply just you actually multiply the Hermitian conjugate of that same operators. And if this is the states, and if you square the state, you need to multiply the conjugate state, which is the Broglie state, which is precisely that state. Okay? And if this is the Hermitian conjugate state, and you should actually reverse this, the Broglie-Katz state, and also put the dagger or Hermitian conjugate on that B operators. Okay, so this is quantum mechanics, Dirac notation. But what is this in the middle? Well, if you simply just look at this operators in the middle, this is B dagger nu B nu, which is number operator. And on two sides of the equation, you get Dirac-Broglie state of N nu and Dirac-Katz state N nu. So by using this eigenvalue equation, the number operator, you get N nu as an eigenvalue times the N nu matrix element, which is 1. Okay, so this is one answer, which is this number N nu. But you could also do the different way by evaluating the destruction operation on the right and also destruction operators to the left. And in both cases, you get B minus coefficient times conjugate of B minus, which is the absolute value square of the B minus. Remember, B plus and B minus can be complex numbers. And then if you pull out this B minus square, you get N nu minus 1 as a Broglie state and N nu minus 1 as a Katz state. And of course, the states are the same, so the matrix element is actually 1. Okay, so on this side you get B minus square, on the right hand side you get N nu. So B minus square is the same as N nu. Okay, so B minus is actually square root of N nu. Since N nu is a 0 positive value, integer value, so this must be greater than or equal to 0, and therefore this B minus coefficient is a non-negative value, which is square root of N nu. We get this answer for this B minus coefficient here. Okay, so let's take a short break. When we come back, we will continue with this B plus coefficient. So let's continue. As I mentioned, this B minus coefficient is fixed as the square root of N nu. And what about B plus? Well, again, that this is your job, that you can show that's B dagger operator acting on this N nu state, you get square root of N nu plus 1 times this N nu plus 1 state. Okay, so the way that you prove this B plus coefficient is in parallel to this B minus coefficient, because you could use this square of this B dagger acting on the N nu state instead of the B acting on the N nu. Right? And then you can use the same trick. Okay, show that this is N nu plus 1 as a B plus square, and then the square root of that. Okay. So I guess that's it. And this is much simpler than this fermionic case. And we know that when we know this coefficient, and you could construct this many boson state, and you can create n bosons out of a vacuum. And when you done that, you could show that this is just the same as a product of many single boson states. And you symmetrize all these single boson wave functions after you make this product. Yeah. Okay. And in a similar manner, when we define the fermionic operators, this is the S plus will be changed to S minus. Remember that. You need to anti-symmetrize the many fermion states. But here it's just a simple, you need to symmetrize all these many boson wave functions. Great. So let's just study a very simple example of such a boson system. As I mentioned in your quantum mechanics course, you already learned this boson, but you didn't notice that. And I already mentioned that some time ago, right? So the simple harmonic oscillator is the first simplest possible example of boson. And let's prove that. Examples, the simple harmonic oscillator in quantum mechanics. But now you could define such a harmonic oscillator in a more solid state fashion. Namely, you can consider harmonic oscillations of the two atoms which formed a molecule. And you can define such harmonic oscillations of a single molecule by the Hamiltonian. Okay, so what is x refers to the relative distance between these two atoms. And of course, this m is actually reduced mass. You know that, right? So now let's just do the simple algebra as a quantum mechanics course that you define this unit scale, which I call this E with a tilde, which is square root h bar divided by m omega. And what is omega? And we'll define that later. Square root of k over n. So now we could define our so-called bosonic operator for a simple harmonic oscillator in the following way. And the destruction operator for boson in this case is a linear combination between x and p operators with the proper units, and also the I in front of the x and p. And B dagger with a minus I in the same way. Okay? Or reversely, x is defined as this unit times 1 over square root of 2 b plus b dagger, and p is actually h bar over e tilde I over square root of 2 b dagger minus b. Remember, this x and p refers to the position and momentum operators in quantum mechanics. So now you could easily verify that. Okay, you have many homeworks today, so I don't give you extra burden. So you could check at home. This is not homework, but you could check your quantum mechanics textbooks. That's the Hamiltonian for such a harmonic oscillator of a molecule is given by h bar omega times b dagger b plus 1/2. And very importantly, you could check that the commutator between b and b dagger is actually 1. Remember, this is not the operator that we defined in the beginning. This is a harmonic oscillator, bosons. So this b refers to the operators, which is here. Therefore, I put this SHO here. So I don't know whether this B SHO or B dagger SHO is a bosonic operator yet. At this point, I don't know until I check their commutation relation as follows. The commutation rules for bosons. Before that, I don't know that, but I assume that this is, I guess, my educated guess tells me that this harmonic oscillator operator B SHO defined this way and that way is effectively a bosonic operator. But up to here, this is only my guess. Okay? My guess is correct only if I could prove that they satisfied this commutation rules. Okay, and they did. They do satisfy these commutation rules. And therefore, this is the proof that this harmonic oscillator problem is actually a problem of a bosonic system, right? So, and you know very well, I don't need to repeat this eigenvalue and eigenstate calculations, and you could check your quantum mechanics textbooks that you can construct this eigenstate one by one, starting from this state 0, which is the ground state, and you construct so-called end boson state, where n refers to the number of bosons and also refers to the energy levels. Okay, so remember that this is your harmonic trap, and you have equally spaced eigenstates, eigenenergies, and the ground state energy is called the 0 state, but you know the state 0 does not have a 0 energy. There's a 0 point energy which is finite, which is 1/2 h bar omega, and this is precisely that value here when you rewrite this Hamiltonian in such a simple form of b dagger b plus 1/2 altogether multiplied by h bar omega. And the distance between the adjacent energy levels of a harmonic oscillator is what? H bar omega, h bar omega, h bar omega, and so on and so forth. And that energy difference between adjacent levels defines the energy of so-called phonon. Okay? Remember that. And the ground state has no phonon. The first excited state, of course, shows one single phonon, and the second excited state actually contains 2 phonons, and the third shows 3 phonons, and so on and so forth. So the thing that you didn't know before today is that the quantum number n that labels the eigenstates in the harmonic oscillator problem is precisely the number of bosons or a number of phonons. So this is something new. This n in the simple harmonic oscillator problem should be correctly interpreted as the number of bosons. Okay, because each boson carry 1 unit of h bar omega, and therefore state 0 refers to no boson state, empty state, and state 1 refers to single boson state with the energy h bar omega plus 1/2, and state 2 refers to 2 boson state with the energy what? 5/2, right? So this is 3/2 for state 1, and this is 5/2 for state 2. Okay, so it's 2 boson energy, 2 h bar omega plus the 0 point energy, 1/2 h bar omega, which is 5/2 h bar omega, and so on and so forth. Okay, so this diagram, energy level diagram, sounds familiar to you, but what you didn't know is that the interpretation of this number n is the number of bosons. And this boson is called phonon. Okay? In this case, it's called phonon. And we will generalize this kind of a simple harmonic oscillator for a molecule to many harmonic oscillator in a solid state, where the ions can actually vibrate in the same way like a simple harmonic oscillator. It's just that they are all coupled together. It's called coupled harmonic oscillator. It's not a simple harmonic oscillator. It's a coupled simple harmonic oscillator. And this is the simplest possible example of boson that is actually realized in nature, because you know that we can consider a real harmonic oscillator motion for a molecule, and molecule do that motion. Okay? And we can understand the energy associated with that harmonic oscillator vibration of molecule, and we can quantize their excitation energies, and such a quantum unit of such a harmonic oscillator vibration is called phonon. And phonon is officially introduced here as one example of a quasi-particle, and which are bosons. And why do we call this phonon quasi-particles? Of course, they are particle-like because they carry integer multiple of h bar omega in energies, but secondly, they are not real particle. Okay, so for electrons and ions, we could see, the presence of electrons as a particle from, say, for example, this STM or some microscope, electron microscope. We can really literally see the structure of atoms, right, distributed in solids. But you cannot really see this phonon directly. Okay, so but of course, photon or the electromagnetic wave or light is also an example of boson. But you can see the photon as a single photon particle. Here, phonon is called quasi-particle because you cannot see directly by any experiments. The only evidence that the phonon exists is this quantization of energy levels. And this is the only evidence that they show this particle nature. And that's why we don't call this phonons particles, but quasi-particles. Okay? So the word quasi refers to two meanings. First one is that they are not real particles. The second is that they are collective motions. They are kind of excitations. Okay? So they do not exist at ground state. Of course, at ground state, there's no phonon because there's no boson here. Boson occupation number is 0. But once you go beyond the ground state, you see this quasi-particle. So there are two meanings of quasi. The first is they are not real particles. And secondly, they are excitations. They do not exist at ground state, but they carry quantized excited state energies, like a particle, but not real particle. So I believe that's probably a very good example that you already learned in quantum mechanics, but you didn't fully appreciate the deeper meaning of those operators that you manipulate. So when you study quantum mechanics, you must have wondered why bother to represent such a harmonic oscillator Hamiltonian in such a clumsy way. But now you should appreciate that. Okay, this is the most elegant way and with rich physics that you really should represent the Hamiltonian of harmonic oscillator in such a way. And you should not solve this Schrödinger equation by brute force for a harmonic oscillator problem, because you don't see that phonon physics if you really brute force solve the Schrödinger equations of harmonic oscillator potential. Okay, this justifies that this is the best way to study harmonic oscillator problem, by mapping this Hamiltonian to the phonon or the bosonic Hamiltonian. And that also justifies our claim that once you start from this occupation number basis, then everything just follows, because you can count this number of excitations, right? So that's the reason why we count them, right? The state 0, there's no quasi-particle. State 1, there's one quasi-particle. State 2, two quasi-particles, and so on and so forth. And at low temperatures, the solid state systems also show such a kind of a behavior where you can really count the your low temperature behaviors by counting the quasi-particle number. Okay, and those quasi-particle number are nothing but functions of Fermi-Dirac distribution or Bose-Einstein distributions. And so this is the only way that we understand many-body solid-state physics. So now you realize something more fundamental and more deeply imprinted in your quantum mechanics textbooks, but you didn't realize that until today. Okay, so there's another example of bosonic quasi-particle is light, electromagnetic wave or photon. So as we mentioned that already, you even know that from your high school that electromagnetic waves are called photons. Okay, but of course you know why they are called photon, because this photoelectric effect by Einstein and so on and so forth, that Planck discovered that this, the electromagnetic wave carry the quantum unit energy h nu, but mathematically or even physically, why photons are bosons. Okay, so of course because photons don't carry spin or spin zero. Okay, and for integer spin they should be called bosons. And by the way, here the harmonic oscillator problem, we also show that we can show that they don't carry the spin, because there's no electron here, right? There's no electron operator. Okay, so the spins must be carried by electrons, and therefore they should be called bosons. But in the following, we should show that these photons are bosons, and they could be the Hamiltonian for electromagnetic wave could be second quantized and map this Hamiltonian onto this very similar form of a harmonic oscillator Hamiltonian. Okay, and therefore the photons shows very similar structure, mathematical structure in Hamiltonian as harmonic oscillator, except they don't have a 0-point motion like harmonic oscillator has. Okay, so and this is our next job. So we erase the blackboard, and when we finish, we start to review your electromagnetic course. Your classical EM course tells you this Maxwell equation and the electromagnetic energies. Okay, and we start from here, and we could second quantize the electromagnetic fields and see that they show this very similar structures as the Hamiltonian for a harmonic oscillator problem. Okay, so let's take a short break. Great, so let's just second quantize the electromagnetic waves or electromagnetic energy. Okay, so this may takes a bit of time, but that's good. So EM wave. Electromagnetic waves are made of photons, but we need to show that photons are really bosons, and they satisfy the commutation relations. Good. So let's try to understand Einstein's photons. And for simplicity, we use the Coulomb gauge, where this electrostatic potential phi is 0, and the divergence of vector potential is actually 0. So you know very well from this Maxwell equation, electric field is minus partial A partial T, where A is the vector potential, right? Which is related to the electric field and magnetic field in such a form. And magnetic field is actually the curl of A, and A is called vector potential. So let's try to write down this normalized eigenmodes for the electromagnetic waves. We know very well that we have some polarizations of electric field and magnetic field, and there's a propagation directions. And I call this x1 and k. So suppose the electromagnetic waves travel along the direction of k, and maybe the electric field is along the x direction and magnetic fields along the y direction, and they are perpendicular to each other. And the three directions are all perpendicular to each other, and they form this kind of right-hand side or left-hand side rule, right? And you could form these three vectors, epsilon 1, epsilon 2, and k, a right-handed or orthonormal basis set. And you could use that basis set to represent this vector potential as a function of real space vector r and time t. sum over k and lambda a k lambda e to the I k dot r minus omega k times t plus a star of k lambda e to the minus I k dot r minus omega k t times this epsilon k lambda, and lambda could be 1 or 2, and omega k is actually the frequency of the light, which is c times the magnitude of the wave number k. So I guess that's the standard form for vector potential, in the presence of electromagnetic waves, right? So there are sinusoidal waves in real space and in time, okay? And therefore, it could be just say the Fourier sum of all this Fourier coefficient, which represents some kind of wave propagation, with the e to the I k dot r minus omega t, right? Where omega is the frequency of the light, and this coefficient a is a function of wave number k and the polarization lambda, which could be either pointing 1 or 2, and the k is the direction of the light propagation. And this is the standard form for the vector potential of electromagnetic waves, right? So that's the say classical EMM. So you could construct a Hamiltonian for such a free electromagnetic fields. Is simply the sum of the electric energy and magnetic energy, right? So from your EMM course, you know that this is given by the integral over the real space of this electric energy, which is 1/2 epsilon 0 times E squared, and plus 1/2 mu b mu 0 times b squared, where epsilon 0 is the electric constant, and mu 0 is the this magnetic moment, right, in the standard unit. So the E squared term represents the electric energy in the EM wave, and the b squared term represents the magnetic energy for electromagnetic waves. If you simply just sum of these two energies, you get the total energy, and you need to integrate over this real entire space, because both E squared term and b squared term refer to the energy density. Okay, so you need to integrate over the real space to get a total energy, which is the Hamiltonian. Great. So now you could simply just take advantage of the identity that you learned from your EMM course, that electric field is actually the time gradient of the vector potential, and the magnetic field is actually curl of A. Okay, and you already defined this vector potential A, and this coefficient here in general can be complex, but the whole thing is actually real. Okay, and therefore the second term is actually the conjugate of the first term. So each of this A k lambda and A star k lambda could be complex, but A k lambda is actually the Hermitian conjugate, so the complex conjugate of A star, or vice versa. The A star is the conjugate of A, so that this product of this A and this exponential vector is actually the conjugate of the second term, or vice versa. So when you add them up, you get the real value, even though each term could be complex, but when you sum them up, you should get the real number. And that's because this vector potential A, it should be real. Otherwise, you don't get physical quantity, measurable quantity, which should be real in value. So we know that this vector potential A is actually decomposed into real part of A plus I times imaginary part of A. And we will see later that real part and imaginary part of A play the role as the momentum and displacement in harmonic oscillator problem. Okay, this is actually P, and this maybe x or vice versa. So I'm skipping the intermediate steps, and you could verify by yourself. The Hamiltonian could be further simplified as the harmonic oscillator like Hamiltonian, where P and Q refers to the momentum and the displacement. Okay, so let me define this P and Q. So P is 2 omega k times square root of epsilon 0 times the imaginary part of A. And Q is 2 times square root of epsilon 0 times the real part of A. Okay, so this Q variable plays the same role of the X and the P as the momentum. Okay, so now you could actually consider this as the harmonic oscillator problem, because you have this P squared term plus Q squared term. And you could quantize this. So this is simply just a classical Hamiltonian, but we could quantize this by demanding that this Q plays a role as the position vector and P as the momentum operator. Okay, so you could quantize this field. And so P and Q satisfy the commutation relations. Okay? And the reason why they satisfy the commutation relations when we quantize the fields, because P and Q are conjugate variables, because you could show that partial Q, partial T is actually P, and partial P, partial T is actually minus omega squared times Q. And from this, we can show that this P and Q are conjugate variables. So by conjugate, I mean this P plays the role as momentum and Q as the position, but P and Q actually have this relation. Okay, just like in classical EMN or classical mechanics, that when we have such relations, and we call this P and Q conjugate variables, and like X and P. So then we could just use that analogy between PQ and PX and to quantize this electromagnetic fields by demanding that P and Q must satisfy the same commutation rules as P and X. Okay, so when we demand such a commutation relation between P and Q, and we can interpret that this, say, electromagnetic energy in this quantized form is nothing but harmonic oscillator Hamiltonian. So, which means that the Hamiltonian for the classical EMN is actually, when we quantize them, it becomes a harmonic oscillator. Okay, so maybe we could stop here for today, okay? And we can continue next time when we finish this quantization or second quantization of electromagnetic wave. And now we can see that there is a close link between the electromagnetic wave and the harmonic oscillator Hamiltonian. Okay? And therefore, we should interpret the photons as bosons, because they show effectively the same type of harmonic oscillator Hamiltonian as the phonon does. So we could end our lecture a bit early today, and so let me just summarize. We learned the, say, definition of bosonic operators, and we show their definitions, the B plus B minus coefficients, and we derived the commutation relations, and we presented the harmonic oscillator problem as the first example of bosons, and they showed integer multiple of h bar omega, and those quantum number n should be interpreted as the number of bosons. And now electromagnetic waves of photons should also serve as the boson particles, and because they have the same form as the harmonic oscillator Hamiltonian, and we will officially study the phonons in solids, okay, where all these springs connecting to all these atoms or ions could be considered as the coupled harmonic oscillator. Okay? You can imagine that all the atoms are connected by some spring constants and they vibrate. Okay? So each of those atoms actually move in a periodic way that's relative to their equilibrium position, and they are all coupled together. Okay? So imagine that you have many balls and they are connected by springs, and when you shake them up, and they will show some normal mode vibrations. And likewise, you'll get some characteristic vibrational mode, which we call different phonon modes. And this really happened in solids. And the fundamental aspects of these phonons are simply just a simple harmonic oscillator motion, but in a more complicated way. Okay, so we should study this more complicated, more realistic solid-state phonons in the following lectures, but we need to also learn the Bose-Einstein condensation for, say, free bosons. Will get condensed in a macroscopic, large-scale wave functions at ground state, which we call the Bose condensate. And we should know what this Bose condensate is next time. Okay, good. So that's it.